Assalamualaikum and good day everyone. Today I'd like to mention the date so that we know what we are in. Today is 17th of May 2021. The time now is around 10:33 p.m. So this is considered week 10 of our course. We are expecting to cover about magnetic material and influence. So I hope you guys see the 22 pages slide. Some of them we'll try to cover this week. First let me go. I will try to using the source from the books and also from the slide. So you'll be hearing clicking sound and hear unnecessary sound here and there. So in this magnetic material and influence, you will at the end of this week, we are expecting to learn about application of the magnetic force, introduction to magnetization, and effect of magnetization, and application of the magnetic boundary condition. In the event that I couldn't teach within these 2 days of class, I will create inshallah I will try my best to do additional recordings and you can watch at your convenience of. So before we in the previous chapters, in the early we learned about electrostatic, right? So now we want to try to learn about the magnetic force. Last time we learned about the electrostatic force. So you may refer to the pages of 352. 352 for these particular chapters. Magnetic force, material, and devices. So we have in magnetic force, we have Lorenz equations. We go straight forward. We call it a Lorenz equation. Where we have actually the force of the magnetics is actually equals to the total charge of the current. This one is total charge on current. So how about if we put this as a magnetic force, we put as M. So it will be more clear, what we are trying to refer. So Q is the total charge on the current, and we will have a U. U is what? U is actually velocity of the moving charge. So U is our velocity of moving charge. If you see this U, right, means it is a vector. And you see the resultants here is also vector. So thus, we need to use cross products, with B. Here case is B. B is where B is actually the, just like in electrostatic, is electric density, electric flux density. So this B is actually magnetic flux density, which we already covered in the previous class, on the 17th on the almost the same day, with previous slide, where we have our B is actually equals to mu naught 4 pi IDL cross R and R cube as the distance, and depending on our depending on our source of current, we might have a difference of A. This is for the line current, this is for the source current, and this is for the volume current. So on current source, then we are introduced also for the current source, we have J, equals to rho V. What is the rho V? Volume charge, right? And then you have mu, and this one is a dot, so you have this. Okay, so this is current density. Is a charge density moving with velocity mu u. Okay, so then we know that we have current source in different we have different type of currents. Okay, so our current element can be for example J dV. Okay, for our current element, and then which we later on we J, you have J is actually rho v u, right? So you just substitute this guy inside. Okay, okay, you substitute here. Okay, then you will have actually J dV is actually a u rho v and dV. Okay, so this is where you do the substitutions. Okay, this one is just an rearrange. Okay, and after that you will find that u is dq. Okay, what is dq? Dq is your from rho v dV. Am I correct? Okay, so it is interrelated, so make sure that you guys are able to see that. And then reading for the slide for detail and the books, okay, you will come finally that you will derive that f, okay, by with this. Okay, you will obtain that f is actually the integral of line I dl cross b. Okay, okay, this is Lorenz equation. This is the magnetic force equation. Okay, however, as you know that we can have three different types of current source, right? This one is for the line current. Okay, so if we want to have this if we have surface and volume current density, we need to change the equation accordingly. Okay, let's say if we have a surface, then if we have a surface density, we would have change a bit the equation to suit the surface situation. So you have a double integral, okay, of Js ds and cross off with your electromagnetic flux density. Okay, and what if you have volume? Then for the case is volume density, okay, so you have f. So sorry for the outside sound, that's why I prefer to record late at night at 2 or 3 or 1 a.m. even though it's a bit tiring. Yeah, it's really tiring actually, because this one is supposed to be a sleeping time, because when we record at daytime, no noise coming from the outside. Okay, so now you can, I think you will be listening to some noise. Okay, so sorry for that. Okay, so for the case of the volumes, you will have a triple integral. Why we triple integral? You guys already get used to it, right? Because it is a volume. So then dV, then cross of magnetic flux intensity. So we need to know that actually B is where the external field, where the force takes place. Okay, takes place. So this is actually the external field. Okay, external field means it is coming from out, not from the one that we are going to sample. Okay. Okay. So I think you guys can read from the slide, okay, there's a lot of them, okay. I just go through, and then you guys know, right, how to determine the cross products, okay. You need to use this right hand like this, okay. So practice, okay, practice. This one will be a bit easier for you guys to actually let's say x cross y, or pi cross alpha, something like that, okay. Something like cross, so you will in the end get to know the products of the cross product by using this, okay. It's a bit easier. And okay, so we go for the books, okay. We just do some reference to the books, okay. So if you can see, there is a force on the charged particle. So this one means this is a point charge, okay. So if it's point charge, certainly it is not integral, okay. It's not integral because it's a point charge, okay. Okay, the electric force E on stationary or moving electric charge in electric field is given by Coulomb's law, experimental law, and is related to electric field intensity. We have E, okay. So this we learned that F is equals to QE, okay. This one is for the electric, this one is for the for the electric force, okay, for the electric force, okay. It shows that if Q is positive, then FE and F will have the same direction. So you need to see the Q, okay. So you also get to know that for the point charge, force on a charged particle, okay, on a charged particle, okay, you get to learn that F, vector F, is equal to QE, okay. So if Q is negative, this means that they are in opposite direction, okay. Opposite direction means your FE and your E is in opposite direction, okay. Then when we expand with in regards of a magnetic force, a magnetic field can exert force only on moving charge, okay, only on moving charge. So remember this, a magnetic field can exert force only on moving charge. From experiment, it is found that the magnetic force Fm experienced by charge Q moving with velocity U in magnetic field B. So we need to consider that actually for this, for the magnetic field, okay, we should consider magnetic field is only on moving charge, okay, only on moving charge, okay. And it is found that the magnetic Fm, magnetic force, experienced by a charge Q, okay, moving with a velocity U in magnetic field B, then you will know that Q equals to U, velocity, cross with your magnetic flux density, okay. So and we know that for moving charge in presence of both electrics, okay, for moving charge, which we can have in the presence of both electric field and magnetic field, okay, force, okay. So the total force, okay, this one is E field, this one is H field, okay, in the presence of electric field, magnetic field. So then our total force experienced by that charge, okay, by that charge is actually F equals to Fe plus of F equals to M, magnetic force plus electric force, okay. So this is what they call, okay, this one, this interrelated, is what they call as a Lorenz equation, okay. So I try to relate with the books and the slides, okay. So expand this, okay, you see this and you see this, right? So you will have F equals to Q E plus U cross B, okay. U cross B is coming from where? Coming from here, okay. Then we factorize the Q outside, okay. Then we have this and this, okay. So this one is taken by your electric and this one is coming from your magnetic, okay. So This one also calls as Lorenz equation, just a extended form. Okay, just a standard form. This one is the simplified form. Okay, so this one is also called Lorenz equation. Okay, now we see, okay, to determine the force on a current element IDL of current carrying conductor due to the magnetic field, we modify using the fact for the convection current. Okay, to determine the force on a current element of a current carrying conductor due to magnetic field. So instead, okay, now for example, for the force on a current element, okay, you guys just please refer to the slide as well. Okay, I will be sometimes using the slides, sometimes using the books, or sometimes using from my own knowledge. Okay, so to determine the force on a current, we have the IDL, okay, of a current carrying conductor. Okay, this one is current carrying conductor. Okay, due to this we will experience, okay, we want to determine the force. Okay, we want to determine the force on a current carrying conductor or current carrying element. Okay, this one is element. Why element? Current carrying element, because we have DL, right? Of a current carrying conductor due to magnetic field. Okay, so we using the fact for convection current, convection current J equals to rho V U. Okay, this one is your convection current. Okay, it's okay, we just put the name, okay, so that we able to memorize it quite easily. Okay, convection current. So we will obtain, okay, okay, and then we try to relate, okay, with our current elements. Okay, relationship between current element like this. IDL is for the line current, this one is for the surface current, this one is for volume current. Okay, volume current. Then combining equation 8.5, okay, which is this equation just now, okay, and these equations, then in the end we will obtain that from our IDL equals to K ds equals to J dV. Okay, this one is our current element. Okay, what types of current element that will be used, okay, depends on the question. So we will in the end derive equation 8.7, okay, which is IDL equals to dq and mu, okay, and u, which is the velocity. Okay, okay, then if for the closed path, okay, we're considering the closed path now. Okay, this shows that element charge moving with velocity u producing convection current dq. Okay, I just want to remind you guys that if it's a velocity, okay, velocity means the acceleration is 0, right? Because this is just some preview, okay, because we might use this in the later on. F equals to ma, right? Okay, a is because the changes in the velocity minus initial velocity over t. Okay, if the velocity is the same, so your a should be 0. Okay, so actually there is no acceleration, it's just a constant moving charge. Okay, so for current through a path, current I, okay, through closed path L or circuits, okay, the force, okay, the force on the circuit, okay, the force on the circuit, okay, the force exists and exerted on the circuit, okay, is the closed integral of your IDL cross the B. Okay. So this will be your another equation. Okay. So you have electric flux, magnetic flux intensity. Okay. And you have your IDL there. Okay. IDL is depends on your current elements. Okay. I try to see if we we learned from on the 27th of April class. Okay, we have DH is IDL. Okay, this is one of the example. Okay, we have the idea. Okay, so then further expand. Okay, I will take some I will do summarization. Okay, because I cannot cover each word on the book, so otherwise we will take more time and maybe not even one semester able to cover if I'm going to word by word like this. Okay, so we will have another extended equation involving this, because this one is for line current. Okay, if we extend it, we will have K ds cross B, which is actually for the surface current, or we can have F equals to J dV cross B for the volume current. Okay, so this one is for the surface current, this one is for the volume current. Okay, because it's cross, so this one is the vector products. Okay, so the force, the magnetic field B, also defined as force per unit current element. Okay, so let me do some a bit so that we will have some time to cover the exercise as well. So force between two current elements. Okay, you can see this is a differential force, mean a small force. Okay, small force between two elements, which is I1 dl1. di1 means I1 at the small differential of length of 1, length 1, and I2 current at the length of 2 differential. According to Biot-Savart law, both current element produce magnetic field. Correct? Because when we do like this, we will obtain the magnetic field circulating. Okay, so we may find the small force. Okay, this one is small force due to the field dB. Okay, small. So we have F IDL times B. Okay, so because it's due to the small force, okay, this one is for the total force. Okay, so the small force, okay, just replace, if we want to, okay, just replace is with the small force. Okay, this one, why is 2 is because this one is external field. Okay, remember just now, where is my external field, where the force take place. So means it's not on the sample, but it's the external field. Okay, remember that what I told you. So better I put the page. Okay, okay, so you can see, right, if we want to do the integrations, you see that your dB, B, you know your dB, how you get the B. Okay, previously you learned, okay, to get the B is that from the previous lecture, where is it? Okay, from the previous lecture, okay, you have your B. This is your B, okay? So your B is mu naught 4 pi over IDL cross R, okay? Over IQ. So it's just the same, okay? It is just the same, okay? So you can see force between two current loop. We can see right here, let's say if we want to take the force between these two current loops, okay, we have two loops here. Okay, you have this differential length. We take a small length, DL2. Then we have a current of I2. Then we have DL, small differential length of 1, and we have current I1. Okay, if you can see this one, the current is moving like that. Okay, so you can see your field is like this actually. You need to look from here, and then here is the field that like this. So actually, if you want to see from this side for you, let's say the eye is here, okay, so you will see that actually this one for this case is like this, okay, and then for this case is like that. Okay, you see it's in opposite directions. Okay, so without further ado, we go to the examples. Okay, I think this one you guys can try to see. Okay, it's raining outside. I hope my voice is still clear. Otherwise, if I stop, then we wait for another recording. I'm not sure when I will be finishing recording. Okay, so we go direct to this practice equation practice exercise 8.1. Okay. I'm not sure if I already shared the tutorial. Okay, if not, I will share, and maybe we can have exercise which is a bit more challenging because tutorial is more difficult. Perhaps. Okay, so we have practice exercise 8.1. Okay, the equation is a charged particle of mass 1 kilogram. Okay, mass 1 kilogram, and a charge of 2 coulombs. So coulomb is 2 coulombs. Start at the origin with zero initial velocity. Zero initial velocity means u naught equals to 0 meter per second, right? In a region where your E is equals to 3 Z, okay, V over M. Okay, so the question now, first, it asking the force on the particle. Okay, so this is actually about the force on the charged particle. Okay, it's like this page. Okay, it's 352. Okay, so what is asking? Okay, you can see that there is element of M. Okay, and there is element of E times 0. Okay, so what we may have is that you can see from here there is M. Okay, not sure if you guys can see this. Okay, so F equals to M du over dt. Okay, so your M, first you do the integration. Okay, you do the integration, you do the differentiation first, your M d over dt. Okay, sorry, is I already write here, why I write it again. Okay, F equals to M du per dt. Okay, and then you also know that here is actually QE plus U times B, and because our U is 0, right, is 0 means it's not moving, initial velocity, so we just F equals to QE. Am I correct? So F equals to, for example, just we continue first to write, and for your understanding. Okay, so because this is 0, okay, so we ignore this. Okay, because this is 0, then we will come that this is Q over E. Okay, understand? Now we just do the substitution. We know that this is 2 coulomb, and it's given E, which is 3Z. Okay, and because this is the force, is a vector, so you should have a direction. So it's a direction of 6Z Newton. Okay, Newton is the standard unit for the force. Okay, now what the question asks us again for practice exercise, the time it takes to reach point P0 12M. Okay, I think this is 12M is a meter. Okay, so the time taken. So if from this, okay, from this the time take to reach point 0012. Okay, so this one will be a bit long. Okay, so B, the time it takes to reach point, so now is P 0012 meter. Okay, so our point of interest, our answer of interest is T. Okay, time to reach this point. Okay, so we know that the equation is du per dt, right? Du per dt, m 1 kilogram. Okay, because kilo is standard unit. Okay, so that's why it's just 1. Okay, so du dt equals to what? You know is actually, you know is already 6Z. Okay, then actually this one also can be, U can be in the elements of Ux, Uy, Uz. And I'm correct? Because this U is actually consists of Ux, Uy, and Uz. Okay, now if we want to consider the movements, okay, with correspond X, with correspond to Y, with correspond to Z. Okay, so we take first, we take du x over dt equals to 0. Okay, then we will get what? We will get ux equals to a. So a is like a constant. Okay, a is like a constant. Then you differentiate du y over dt. Okay, again you make it 0. Then you will get a constant of uy in b. Okay, then for duz, why does it mean that uy ux? Because we have we might have terms of x or y or z inside. Okay, so for dz dt, let's say it's 0, it's non-zero. Okay, because we have 6z here. Okay, it's 6z du, so you have 6. Okay, you have 6, so you have u in terms of z, you have 60 plus c. Okay, so this is actually the results of the differentiation. Okay, 0, 0, this one. Okay, this one is actually where you actually get it from the integration. Okay, so dux 0 because there is no x here. Du over dt 0, and du over dz, you have 6z, you have c. So when you do the integration, you will get a constant here. Okay, now, and since it is given that u naught, okay, is 0, okay, initial at the time of 0, okay, given that mu naught, I just put here like this, okay, you can use anything, okay, at t equals to 0 is 0, okay, it's mentioned at initial, it doesn't move, right? And then so ux 0 and uy is also 0, okay. However, uz equals to 6t, okay, plus c, okay, this one we have element, okay, means we have element of t. So however, let's say at time 0 it's mentioned it is 0, right? So at times of 0, this is 0, so your c. So your c is actually 0. So you end up uz is actually equals to 6t only, okay? So far so good. Then there we have uz equals to 60, correct? Okay. So and you from here, you know that your a, your b, your a, your b, and your c is equals to 0, okay? Okay. Okay.